Welcome to The Explainer. Today, we're tackling a concept that honestly sounds like it belongs in a sci-fi blockbuster, but it's literally driving the reality we live in every single day. We're demystifying machine learning. And to do it, we're going to use the absolute best mirror we have, ourselves. We're going to explore how machines learn by comparing it directly to how we humans learn. It's a pretty wild journey, so let's just jump right in.
So, our story actually starts way back in 1950 with the legendary mathematician Alan Turing. He posed a super simple but completely world-shifting question. Can machines think? That one little question set off a massive chain reaction of cultural milestones. Fast forward to 1997, IBM's Deep Blue computer absolutely shocked the world by taking down the reigning chess champion Garry Kasparov. And get this, to put it in perspective, Deep Blue was evaluating 200 million positions per second. Kasparov, he was processing maybe 5 to 10. Crazy, right? And that momentum just kept building. Right up to 2016, when Google's AlphaGo did the unthinkable and beat a professional human player at Go, which is a mind-bogglingly complex ancient game.
Now, what's really interesting about this slide is that we almost always talk about machine learning like it's this brand new tech trend that just magically appeared overnight. But the roots, they run really deep. Right after Turing threw down the gauntlet, a guy named Arthur Samuel over at IBM built the first machine learning program that could play checkers. And that was way back in 1952. So yeah, we've basically been building up to this modern AI explosion for well over 70 years.
Okay, so here's our roadmap for the explainer today. First, can machines actually learn? Second, human versus machine learning. Third, the machine learning process. Fourth, supervised learning explained. And finally, unsupervised and reinforcement learning.
Section 1. Can machines actually learn?
Okay, let's dive into this. Section 2, human versus machine learning. Now, in cognitive science, learning is basically just the process of gaining information through observation so you can improve your efficiency. Whether it's a kid doing math homework and making fewer mistakes over time, or scientists tweaking a rocket trajectory based on fast data, learning is really all about using past info to do a task better the next time around. So how exactly does human cognition stack up against machine cognition?
Think about how you learned stuff growing up. You probably learned in 3 main ways, right? First, you had expert guidance, like a teacher showing you the alphabet. Second, you applied past knowledge. Knowing the difference between a noun and a verb so you could write a totally new sentence. And third, self-correction. Like a baby falling down over and over until they finally figure out how to step over an obstacle. Well, machines mirror this exact same process. But instead of school teachers and scraped knees, they do it powered by input data, abstraction, and generalization.
Section 3, the machine learning process. Let's look under the hood and see the specific 3-step flow algorithms used to process all this data. As you can see, the essence of artificial cognition boils down to this 3-step flow. It kicks off with input data, gathering past information. Then it moves into abstraction, where a conceptual model is built. And then it lands on generalization, which is the magic moment where the machine actually applies what it learned to new, unseen data.
The absolutely crucial point here is that middle step, abstraction. Think about it. Imagine trying to literally memorize every single living animal on Earth. No way, it's impossible. Instead, as humans, we abstract them into broad categories: mammals, reptiles, birds. If it has fur and is warm-blooded, boom, it's a mammal. Machines do the exact same thing during this abstraction phase. They create a generalized model, so they aren't forced to just rigidly memorize millions of individual data points. They learn the rules, not just the answers.
And that brings us to this definitive quote from Carnegie Mellon professor Tom M. Mitchell. He basically took everything we've been talking about and distilled it into this perfect logical formula. He says a program learns from experience E with respect to tasks T and performance P if its performance at tasks in T improves with experience E. And now, it sounds a little bit mathematical at first, but it perfectly captures the very essence of artificial learning. Let me show you what he means. And this brilliantly illustrates Professor Mitchell's formula using Arthur Samuel's classic checkers example. The task, or T, is simply playing the game of checkers. The experience, E, is the database of all those past games the computer has access to, and the performance, P, is just the percentage of games the computer actually wins. So, if giving the computer more past games, literally more experience, increases its win percentage, well then boom, the machine has officially learned. Section 4. Supervised learning explained. Because now that we know how they learn, we need to look at the different schools of machine learning. If you look right here at the machine learning family tree, it essentially splits into 3 distinct branches: supervised learning, unsupervised learning, and reinforcement learning. We're going to start by walking down that first branch.
Basically, supervised learning is predictive learning. It's exactly like a parent teaching a child their colors. The parent points to a blue toy and says, blue. They point to a green shirt and say green. They are literally providing the labels. In supervised learning, a machine is trained on a massive data set of these past labeled examples. And because it relies entirely on those specific labels, the machine's prediction is highly dependent on the quality of that training data.
Let's move to the next step and see how this builds. You have this massive database of labeled training data flowing into the machine. The machine acts as the supervisor, guiding the creation of a prediction model. Once that model is fully built, you can hand it completely new, unlabeled test data, and the model will confidently spit out a prediction based entirely on what it was taught.
Now, within supervised learning, there are 2 main subtypes, depending on what you're actually trying to predict: classification and regression. Classification is all about predicting a specific category. For example, a bank using an algorithm to classify a transaction as fraud or normal, or a healthcare model classifying a tumor as malignant or benign. Regression, on the flip side, predicts a continuous numerical value. So think of forecasting next year's sales revenue or predicting real estate prices based on square footage.
Let's actually look at the classification model in action. Here, the labeled training data includes individuals with scores for aptitude and communication, and then a resulting class like speaker or intel. The machine analyzes and learns this relationship. So later, when new test data comes in, let's say a person named Josh walks in with an aptitude of 5 and communication of 4.5, the model can instantly classify him into the intel category based on those exact attributes. It's organizing the unknown based on the unknown.
Section 5. Unsupervised and reinforcement learning. Because what happens when a machine doesn't have all that neatly labeled data handed to it?
Yeah, supervised learning is great when everything is neatly labeled, but if a machine is just handed a mountain of raw data with absolutely no labels, no tags, and zero guidance, that is where unsupervised learning steps in. It's descriptive rather than predictive. The algorithm looks at this massive pile of raw, unlabeled data and is basically told, go find the patterns. It relies purely on finding natural groupings. A classic real-world application of this is customer segmentation in marketing. A company dumps all its customer data into the system, and the algorithm naturally segments those customers into very specific buying groups that the human marketers might never have noticed on their own.
And finally, we have reinforcement learning. This is where a machine learns to achieve a given goal purely through trial, error, and self-correction. Remember our analogy of the baby learning to walk? That baby isn't getting direct instructions on muscle mechanics, right? They just try, fall down, realize that was a mistake, self-correct, and try again. Reinforcement learning algorithms do this exact same thing, just inside digital environments. To really bring this to life, think about Sony's robotic pet, Aibo, launched way back in 1998. Now, Aibo wasn't just some pre-programmed toy. It actively used reinforcement learning to figure out how to navigate its environment, express emotions, and it even learned to recognize its owner over time, all through trial and error interactions. It was so groundbreaking that Aibo actually got inducted into the Robot Hall of Fame at Carnegie Mellon in 2006.
So, from Alan Turing's theoretical question back in 1950 to algorithms predicting real estate, spotting banking fraud, or powering robotic dogs, machine learning is fundamentally just a digital mirror of our own human learning process. I want to leave you with this final thought. Look around your life right now today. The shows you stream, the emails filtered from your inbox, the highly specific ads you see. How many of your daily digital interactions are quietly being driven by these exact algorithms? Keep your eyes open out there and stay curious. Thanks for joining me on This Explainer.